I'm running into a small technical problem. I might have to, there we go. So let's fire up this.
So I'll kind of fade in the background here, Chuck, and I'll let you kick it off whenever you're ready.
Okay, thank you. I see it says 3 o'clock, folks. So everybody's on now, Jen?
We've got 8 folks joining us. I imagine folks will come in, but that's okay. It's 3 o'clock.
Yeah.
We can get started.
Yeah. All right. And Steve, we're going to wait for you to share for a moment here.
All right.
Okay.
That's fine. I'm just figuring out where I'm going here. So.
Yep. And while that's going on, so I'll introduce myself. I'm Chuck Tennyson, and I'm with the Driftless Area Land Conservancy. We are so grateful that we have folks interested in these topics that are very exciting to us. And the presentation, this series of energy-related presentations is being sponsored by us, the Driftless Area Land Conservancy, and the Dodgeville Public Library. We had initially thought we'd be holding these in person. The library was very gracious to co-sponsor with us, so we might get there yet for some of the ones in June, we'll see. So we are going to begin with just a short presentation by one of our board members, Dick Cates. Are you with us, Dick? And maybe not. We won't start with that. But I'll tell you what.
I don't see him, Chuck.
You don't see him?
Mm-mm. Oh wait, this might be him. Hang on.
I hear you. I hear
good.
you. Yeah.
Oh,
yeah,
good.
I've been here.
You've been here. Okay.
Yeah.
So can we, if I share screen here, Steve, do we have to have yours off of there? I'm
trying to figure out how to get myself back up here. We'll take that off. There we go.
There we go. Okay. Well, oh, no, where am I here? All right. Well, I'm going to introduce Dick Cates here, and let's see if we can get his picture up on the screen here for you folks. Not being successful. Let's see if I do, oh, shucks. There we go.
There we go.
Does that work? There's Mr. Cates. Thank you.
Aw.
Looks good.
Thank you, Dick. And sorry
Yeah,
for those of you that are with us here, the technology's coming along. Well, Dick is one of our board members. He's been quite interested in this energy district concept. He's been helping us move it forward. Dick is a local farmer, sustainable agriculture expert in our area. He's an adjunct professor at the University of Wisconsin-Madison. He speaks widely on sustainable agriculture throughout the world and writes on that topic. We are so grateful to have him on this board and our board, and of his great interest and knowledge about energy districts. And with that, we'll have Dick give a short introduction of what this concept is that we are working toward with local activists here in the area and with through Driftless Area Land Conservancy. And then Dick, when you wrap up, we'll introduce Steve Nyland, our main speaker for the day. So Dick, take it away.
Great. I trust you can hear me okay, folks?
We can.
Okay. So for those who have been on this series previously, I guess you can put your heads down and rest for 5 minutes because I'm going to essentially repeat myself. But every week I learn more because this is a process. And right now we don't have an energy district, although we are working towards an independent renewable clean energy district for the greater Iowa County. I think what we have now, and I like Alan Pincus's terminology, a greater Iowa County Clean Energy Alliance, and we're exploring options for local ownership and control of a clean energy future in Iowa County, and we are in that process potentially laying the groundwork for the establishment of an Iowa County Energy District. And in speaking with the individual who started the first energy district in the country, Andy Johnson, in Northeast Iowa, Winneshiek County, he basically said in a nutshell that the goals for the most part are local ownership of a clean energy future that's just and inclusive. And I think that embodies the values of our group as we're getting together over these months. We're learning every month we get together, we're learning more. But just quickly, the notion of an energy district is essentially based on the model that's in place since the 1930s, when we had another very, very significant need. That is, we had tremendous soil erosion from the Dust Bowls in the western part of the United States, and too much rain here in the Driftless area where our cropping patterns didn't cover the soil, and we had to come up with a way to deal with this problem. And the notion was a conservation district, and in a nutshell, it's partnerships of private, local, and also government entities, whether they be county, state, or federal, to come together to solve a problem. And a neat term that Andy Johnson's Winneshiek County Energy District came up with was something called a flywheel of momentum, or a flywheel of change. And so there's a lot of pieces that happen, but there's energy planning, there's public engagement, there's market transformation, advocacy at the policy level. And once there's a committed group of individuals who have a mission statement and goals in mind, this flywheel of momentum starts to gain traction. But again, just capturing the overall concern is that right now we all pay money for to heat our homes, to move our vehicles, to everything we do. We purchase energy, and then that money goes out of our communities. The notion of an energy district is locally owned, as I said, just an inclusive, clean energy future. So to keep that money locally, and that is a strong economic engine, which all of us in rural Wisconsin know. There's nothing that can be more inspiring than to help our rural economies help us help ourselves. Is that the way I will say it? So with that, I'll thank you for the time.
All right. Well, thank you for that introduction, Dick. And let me introduce our main speaker for the day. We're so grateful to have Steve Nyland. Steve's the Vice President of Energy Systems Engineering for Decentrix, which is an affiliate of Faith Technologies. He is the one responsible for supporting the vision, the development, growth, and execution of Faith's energy delivery strategy. We'll be hearing more about that. The goal is to ensure that clients have the most cost-effective and resilient electricity delivered from an electrical infrastructure that prioritizes the use of all available resources, such as renewables, energy storage, and the utility grid. Throughout Steve's career, he's led multiple efforts in product development, automation, operational transformation, sustainability, lean quality system development, and renewable energy across a variety of industries. Steve we are very lucky to have someone who has such an extensive background in all these kinds of things that we've been exploring through our series here of presentations. So with that, Steve, if you want to give that screen share a try again.
We'll give that a shot, and
it looks good.
you look good. All right. Well, thank you very much, Chuck, for the introduction. Just a little brief background about Faith. So we are the energy division for Faith Technologies. We work in distributed generation and microgrids, and we'll be talking a little bit today about what that distinction is between those. From a standpoint of scope, we do anything from systems that are less than 20 kilowatts up to 130, 150 megawatt utility scale systems, everything in between. We work in wind, solar, hydro, energy storage, combined heat and power, all things that we'll be talking about today. So we have a wide breadth of experience in a number of areas. We work with private enterprises. We work with public enterprises. We work with the utilities, both regional electric co-ops and bigger utilities, and helping to deliver energy solutions. We do this across the country. We have 20 offices across the US. We are practiced in every state of the United States. We're the 10th largest electrical contracting firm, our electrical contracting division, and we're the 20th largest electrical design firm in the US. So that's my Faith commercial. So let's talk about energy. So I want to talk about the current state of distributed generation technologies. So distributed energy in the United States, per the EPA, this is based on a 2007 study and a 2012 follow-up study. Per the EPA, distributed generation resources now produce about 1/6 of our capacity of the nation's existing centralized power plants. Actually, that's gone up a bit. So think about that. 1/6 of our energy already comes from distributed generation. So what are we talking about? You know, if we look at the illustration here on this slide, traditionally we've had centralized power. For instance, I live here in Green Bay. About 3 or 4 miles from my house is We Energy's coal-fired plant up here in Green Bay. That would be a classic example of centralized power. If I go a few miles down the highway towards the Fox Valley, towards Appleton, in the Kaukauna area, there's a large natural gas peaking plant there that's utilized when I need to pick up some additional load. So that's an on-demand plant. Go just a little bit farther into Kaukauna, and Kaukauna Utilities has a hydro plant on the Fox River, generating power there. All those would be considered normal, centralized, traditional power sources. What we're talking about today, when we talk about clean energy districts, is localized clean power. If you look at the illustration on the right, so it's a combination of looking at local PV, smaller generation assets, can be as small as on a residence, could be as big as a multi-megawatt installation. It can be wind, it can be a combined heat and power solution. So picture a generator or a microturbine that's producing electricity and also producing heat or cooling to be utilized maybe by a commercial building or from an industrial manufacturing facility. We're seeing more and more, as we see 1/6 of our capacity is coming from the, but why? Why is now the time we're seeing this? Well, first we need to talk about our energy landscape a little bit. So the energy landscape is changing. First of all, we're becoming more electric. We're getting away from fossil fuels. We're seeing more EVs. We get involved in EV charging solutions here at Faith also. Seeing a lot of impact on electrical vehicles. To the tune of growth is going 2 times faster in electricity than all the energy types combined by 2040. We're becoming more digitized. So we have 10 times more connected devices than people by 2025. We're all aware of that, right? So if I look around me right now, I have a cell phone, I have a laptop computer, I have another cell phone, I'm connected to my Wi-Fi network. I recently, about a year ago, bought a refrigerator, and the salesman goes, "Do you want a cloud-enabled refrigerator?" And I'm like, "Why would I want a cloud-enabled refrigerator?" And the salesman says, "Well, if you're at work and you decide there's a recipe you want to make for dinner," he said, "you can pull out your iPhone, you can pull out your computer, you can log into your refrigerator, which also stores all your recipes, pull up the recipe. You can then turn the cameras on inside the refrigerator to see if you've got everything you need for the recipe. If you don't, you can log onto Woodman's or Pick and Save's website, order the groceries you need, have them delivered at 5 o'clock on your door, and your refrigerator can also tell your web-enabled stove when to turn itself on to make sure the oven's preheated for you." I said, "Yeah, thanks, I'll just take a regular refrigerator." But it's a good illustration of how many connected devices. Think of, if you've got 2 or 3 TVs in your house, typically nowadays those are connected devices. 10 times more devices than people, and every one of those devices takes electric energy.
Steve,
At the same
Steve,
time,
I'm just going to interrupt for a moment here. We've had several people join us since the very start, and just wanted to remind folks that they can, if you have questions, you can write them in the chat, and Steve and I will see those, and we'll, if they are apropos to the very topic he's just talking about at the moment, we might interrupt and take some of those, or otherwise we'll save them for the end. So feel free to add your questions in the chat box, and take it away, Steve.
all right, thank you, Chuck. So at the same time, we're creating more demand. The traditional grid is aging. You may have noticed, I know I noticed in this area, we're seeing more short-term and longer-term power outages. And also those traditional generation assets are expensive. So if I look at, it's trying to site a new power plant. Let's say I wanted to build a new coal-fired power plant. By the time I pick a site, go through design, go through all the licensing, it can take any place from 10 years on up to finally get that site picked out, built, commissioned, and online. It's a long time, and it's a big investment. At the same time, we're also trying to become more decarbonized. We're trying to become greener, right? We're trying to get away from those traditional fossil fuel-based plants, that coal plant that I have up here in Green Bay, a few miles away, or that natural gas plant. And we're trying to become more decentralized. Again, if we're able to spread these assets out, the more we can spread out the assets, the smaller impact we have if we have a problem with the grid. Picture if you're PG&E and all the problems they've had with wildfires. And if I lose a transmission line, I lose tens of thousands of homes. Now, if I put distributed generation within those communities, I lose a transmission line, most of those communities I'm able to keep up because I'm able to supply them locally versus those long distance transmission lines. Think about up here, the transmission, that power plant that's here in Green Bay, that supplies power to most of Door County, between that and the plants over in Two Rivers. So if I lose one of those plants, I can lose most of Door County. There's long transmission generation. All that transmission generation creates inefficiency also because I have line losses. One of the interesting facts, if you look at the power that's delivered to your outlet in the state of Wisconsin, the average percent efficiency of the electricity at your outlet is someplace between 35 to 45%. That means most of the energy without that original source, whether it's coal, whether it's natural gas, whether it's nuclear, has been lost someplace down the line. It's been lost if I'm the plant here in Green Bay and burning the coal to generate steam, to push a turbine, to go through transformers, to go through the long lines, to get to the outlet at my house. By locating assets more regionally, more closer, by decentralizing, we're also able to decrease those losses in the system also. and boost up our overall efficiency. So why else now? Well, we've driven down the cost of renewable technologies, and we're going to focus in on a few of those items. Governmental policies are becoming more favorable. We're looking for increased resiliency, and we'll talk about that a bit later too, and some of the things that have happened in our state within the past year. And finally, we want to reinforce the grid. We want to be able to help support that grid more. So maybe we can cut back on those numbers of outages we're seeing also. So renewable energy costs, you know, we've seen something interesting in the last 10 years about where renewables have gone. So if you look at the illustration on the right, both of these are based on levelized cost of energy. So what's the lifetime levelized cost? Includes the original capital to produce the energy, includes the ongoing operating and maintenance expenses. And as we see, we've seen a significant decrease in wind over the past 10 years. Decreased price to generate wind is down 70%. Solar has decreased by 88%, and it's still going down yet. Much less, much less of a slope than we were, much more gradual change, but it's still dropping. At the same time also, if you look at energy storage, our nice red line right here, energy storage has dropped 75%. So that makes wind and solar more feasible as 24/7 solutions. You know, you've heard it said, I'm sure, that, well, the sun doesn't always shine and the wind doesn't always blow. And that's true. But generally, most areas, when the sun's not shining, the wind is blowing. And if they both aren't, we can store energy. And when we talk about energy storage, and we talk about battery storage, and we talk about different ways of storing, it's just another form. If I talk about the coal plant here in Green Bay, there are big piles of coal sitting outside of that plant. That's just another form of energy storage. Batteries are just another form. We store energy all the time to be able to fire our infrastructure on our grid. Just another form of doing that. The bottom line, when we look at these alternative energy solutions, these distributed solutions, and we compare them to the cost of the levelized lifetime cost of conventional energy sources, we have hit a point where we're very competitive when we start talking about commercial, industrial, utility scale installations, and we're starting to push it even from the residential. Again, if we look at this top graph, all of these technologies here are competitive or better than the technologies we're seeing down here. So it's starting to make sense from a utility standpoint, and we see that, right? We see more utilities installing PV. We see more utilities installing energy storage. We see more utilities installing wind assets. Look at the large wind farms we now have in Wisconsin. It's making sense because I can do it faster and I can do it cheaper than I can do a conventional power plant. So what's happening from a governmental policy standpoint? Well, we now have 37 states, the District of Columbia, and 3 territories have established renewable performance standards or goals. Nice little map we have on the lower right. Anything that's colored in dark green, they have actual standards that utilities and or private parties are required to meet within the state. For instance, if we look at California, any new construction for residential construction in California is required to have a solar component now. The lighter green colored states all have voluntary goals. Most of these states target between 10 and 45% renewables, most of those in the next 10 to 15 years. 7 states and Washington, D.C. have requirements of 50% or more. And we currently have 145 cities that are committed to or powered 100% by renewables. All this has happened within the last 10 years. So what are the challenges?
Steve,
Biggest,
I'm going to
yes,
interrupt again. I think we've got a good question for your 2 slides ago. Judith
absolutely.
asks about subsidies. Can you make any comments about how those subsidies to the fossil fuels and how they compare with current subsidies for renewables?
So if you look at renewables, especially PV, wind, energy storage, if it's tied to one of those generation sources, you know, we have some pretty favorable tax advantages right now with the investment tax credit. Some of the things around accelerated depreciation. So that makes it very, you know, it makes it right now for those types of systems favorable compared to fossil fuels. Now, some of those are phasing out. So we have we're currently in a phase out period for solar for that investment tax credit. We're at 26% this year. We dropped to 22% next year. Then I am trying to remember because I haven't looked that far out again, 17, and then I believe 10 after that. And then at 10, it'll stay fixed. The idea being that technology is becoming more cost effective. The cost per watt of delivered power is dropping. So the idea is the tax credits, the subsidies that are there help to compensate for a high cost until the volume is driven to a point where the cost is driven down, which makes sense. There also are a number of programs when it comes to rural areas. For instance, the USDA has something called their REAP program. And the idea of that is to encourage the development of renewable assets in agricultural rural areas. And that you can get about a 25% grant towards the cost of any renewable project. So we do have some pretty decent subsidies, you know, in comparison to what the fossil fuel industry is. Unfortunately, though, the fossil fuel industry does tend to have better lobbyists. And so there are some additional benefits they get, but in spite of that, we're looking at renewables at this point are able to be very competitive. Does that help answer a question? Any?
Yes, I mean, I'll just add a little supplemental there. I mean, I'm not very knowledgeable about this, but we hear about subsidies for oil exploration and tax benefits, you know, if they, for these expensive explorations and coming up, you know, sometimes they amount to nothing and such. Do you have any comments about that?
Yeah, you know, I guess, you know, Chuck, I can argue 2 ways. I mean, one, it's you know, do we fund on par with renewables? I will say, you know, the government does give some decent research and development credits for renewable development. Is it on par necessarily with what again happens with fossil fuels? No, I think we could probably get more parity there. What I will say though is for the dollars that are invested, we tend to get a better return on the renewables than we do on fossil fuels, because as you point out on oil exploration, quite often that exploration ends up with no real benefit from it. So there is more risk I can see. And at the same time too, we want to make sure we're able as a country to preserve some amount of energy resiliency and independence. So we don't have to depend on maybe some other countries for our fuel needs. Again, the more we can increase our renewable portfolio though, the more we lessen that need for those fossil fuels also.
Excellent, thank you.
Sure. So what are the challenges towards renewables? Well, first we have a really complex matrix of local, state, and federal policies and regulations. It's very regionalized. When we start looking at projects, we need to look at not just the state the project is in, but the utility of the project, the utility that services the area that we're looking at the project, and often what the local municipality is doing also. So it's very complicated. What works as a project in one area doesn't work as a project in another. For instance, in the state of Wisconsin, I can build an energy system, I could lease an energy system, or I could sell an energy system to you, but I can't sell you power unless I register as a utility. In the state of Minnesota, I can execute something called a purchase power agreement, and I can basically build an installation, and instead of charging you to build it or leasing it to you, I can just charge you an electric rate for generation. One area has incentives, one area doesn't. State of Wisconsin, anything involved with solar generation, so solar panels, solar inverters, racking systems, all are exempt from Wisconsin state sales tax and property taxes. I go to Illinois, they're not exempt from sales tax. Everything changes. What I'm able to do from a standpoint of, can I sell energy back to the utility at an area or can't I? Those rules are all over the map. Even within the same utility, they can be drastically different, depending on the location. So we have that piece. We look at solar and wind installations. They do require space. Quite often some significant amounts of space. I mean, we're talking about, if I'm talking about a multi-megawatt system, I'm talking about acres of land. So I need to find open land. I need to try and design systems that have as little environmental impact on those spaces as possible. Also, from a standpoint of wind, it's difficult to site, especially, I don't know the problem people have with wind. Wind is very safe, it's very quiet. It doesn't kill birds, contrary to popular belief. You know, if you've ever looked at a wind turbine, they actually turn pretty slow. But they're difficult to site because I need a laydown area. I need to be able to drop that tower if I need to service it. So however the height is of that tower, I need that radius around the tower. And there is also a certain zone I need outside of that. On top of that, the FDA gets to weigh in on where wind towers are sited based on how tall the towers are. And most jurisdictions have some amount of local control too. So it can be difficult to site those. Technologies that utilize combustion of fossil fuels can produce many of the same impacts as the larger fossil fuel power plants also. So I need to make sure that I'm looking at clean sources. If I'm going to do a combined heat and power, if I'm going to put a genset in, I need to make sure I've got the right controls and the right cleanup on that genset. So I'm not just moving the problem from one location to another location. I want to make sure that I'm cleaning my exhaust, for instance, as much as possible. If I look at waste incineration, we've got a lot of landfills that will generate biogas, mass combustion. Combined heat and power may require water for steam generation or cooling. So I may be saving energy, I may be able to get local sourcing, but now I need more of a water source. So that may limit where I want to locate that generation so I'm next to a large body of water so I don't affect an aquifer. How do I handle the balancing of generation assets within the larger grid? So I can't over-generate in one particular area unless there's a way for the utility to move the energy from that area to another area. One of the things that we do when we do larger energy systems, we work with utilities and we run impact studies because we have to know if we're not able to consume everything on site. For instance, let's say we put in a large 2 or 3 megawatt system for a manufacturing plant. And the manufacturing plant only runs 5 days a week. What happens to that energy on Saturday and Sunday? Can the utility take it? If they can take it, how far upstream? Can they take it on the branch that that particular installation is on, or do they have to figure out how they can take the energy back beyond their substation and into their wider network? So we need to look at impact studies on how we can handle that and mitigate that before we're able to build the installation. And last, we need to help utilities develop an equitable business model. I mean, utilities, they're not in business to be a charity, and quite often, you know, there's a kind of give and take that kind of doesn't happen between people looking to do their own generation and utilities. And we have to understand the role that utilities and the role that the larger grid does play. A lot of people want to have their cake and eat it too. I want to put in generation assets, but I still want to be able to fall back on the utility, but I don't want to pay them anything for having that backup for me. It's like, well, no, you have a value, and it's fair for the utility to be compensated for that value, for that backup. I'm going to pause for a minute, Chuck, if there are any other questions. Well, we got you muted. Your mic's muted, Chuck.
Thank you.
There you
Sorry
go.
about that. Yes, it was. So no new questions. A response from Judith thanking you for answering her question. And she just responds that she's glad to hear you clarified the wind impact. The land conservation community could help spread that message. Many folks don't like the way they look, but they're very compatible with farming too. So
Exactly.
just a comment.
Yeah, again, because you need to keep that clear space around a wind tower. It's very, very attractive in agricultural areas, right? Because I have the open space anyway. So let's talk about what distributed generation is. So to understand that, first of all, let's talk about what a microgrid is. So a microgrid is a collection of energy resources. It can be generation, it can be solar, it can be a wind turbine, it could be a hydro system. It's a storage system, someplace to store the energy, and loads. And the important things are here is the storage system is the important component here. It presents itself to the main grid as a single, flexible, and controllable unit. So it's when the utility sees it, when the grid sees it, there's one connection point. I may have a half a dozen generation and storage assets behind that, but there's one interaction with the utility. And I can control what I can take or put back to the utility. But I can also disconnect this thing, or maybe I never connect this thing, and operate it autonomously without the grid at all. As opposed to that, local energy resources that don't have storage, that can't operate autonomously, aren't microgrids. They're just distributed energy resources, or we call DERs. And that's an important distinction, and we'll talk about what that distinction is as we move forward here. Because a lot of people will put in distributed generation and think they're getting something they're not. So distributed energy resources, what are the benefits if I just get some energy resources? Well, they can be components of a microgrid, but in and of themselves, they're not microgrids. And we'll talk about that distinction because it's a very important distinction. They can, however, provide cost savings. So if I install a solar system on my house and I'm able to generate some or all of my power during the day, I'm going to offset that cost from the utility. I can do demand shift. I can do demand shift or demand balancing. So if I'm an industrial customer and I get charged for demand, demand is we would like to refer to as the just in case charge. So if you are a large consumer of electricity, there's a charge you pay per kilowatt hour to ensure that that electricity, that capacity is available from the utility. Whether you use it or not, you pay that every month. So by putting in a storage system on site, we can shift where that demand goes. So in other words, I can put solar and a battery system in, I can charge the battery system during the day and discharge at night. Or if I get a really favorable electrical rate at night, I can just have a battery system. I can charge it during the night when I get that low electric rate, discharge it during the day when I have that higher rate, and cut my demand down. We can use it for peak shaving. The other thing that affects that demand is peak shaving. So the utility looks at the highest demand that I have within a year in kilowatt hours during my demand period during the day, in the state of Wisconsin, for instance. And whatever peak that hits, that's the demand rate I'm charged for the rest of the year, whether I ever again come close to that peak or not, because again, they want to make sure they have the capacity if I need it. By, again, using energy storage, I can cut back on how high that peak goes up by discharging a battery when I start to see a rapid increase, or I start to see myself approach a certain threshold value in electric usage, and therefore clip off that peak and lower those demand charges again. And I can provide some grid reinforcement. I can help strengthen the grid within my facility. So I just bumped my mouse. There we go. So we have a lot of different types of distributed energy resources we can work with. Everybody's familiar pretty much with solar panels, with wind turbines. We can utilize generator sets. We can utilize natural gas or diesel. Microturbines, if you think of a microturbine is a jet engine, basically. They tend to burn pretty clean. And depending on if we're doing combined heat and power, if we're trying to recover the waste heat from a generator or a microturbine, it's another source to get some of that waste heat, which I can generate either heating or cooling from that waste heat. If I need more electricity than heat, I'll tend to go towards a generator solution. If I tend to need more heating than electricity, I'll look at a microturbine. Microturbines generate more heat than electricity. Generators generate more electricity than heat. Fuel cell and electrolyzer system. So I can take electricity from solar. I can run an electrolyzer. And if you think of what an electrolyzer is, if you think back to 8th grade science class, and if you ever took the experiment where you took like a 9-volt battery, like a camping battery for a lantern battery, for those of you who might remember those, and you put 2 electrodes in a beaker of water, and you had bubbles that came up. And if you look at what that is, one electrode has hydrogen that's being gathered there. The other one has oxygen. That's what an electrolyzer does. It generates hydrogen from water, that same process through electrifying it. We store that hydrogen, and then we can take that back through something called a fuel cell. What a fuel cell is it's a membrane electrolyte system. I push hydrogen through the membrane. It strips off the electrons to generate electricity. And then the hydrogen that's left combines with oxygen from the air to generate water. So if you look at that whole cycle for generating the hydrogen and reusing the hydrogen to generate electricity, if I generate that with solar, I basically got a totally green system, aside from the initial carbon impact of producing the components. And it gives me a way to store that fuel. I can store that hydrogen, and I can store it for longer periods of time necessarily than maybe I can store battery energy. Or it's something that works more effective in certain climates, because I can run an electrolyzer, let's say in Anchorage, and store that hydrogen for a long period of time. Battery systems, not so much, because if I get in a cold climate, I've got to keep that battery system heated at least to a certain level to have it be effective. The hydrogen I store in that tank doesn't care. Energy storage systems, batteries. Lithium-ion batteries, zinc hybrid batteries, lead acid. Lead acid are like the batteries you see in your car. Flow batteries. Flow batteries are interesting if we can ever perfect the technology. So in a flow battery, I have an electrolyte, and I basically take some type of generation source like solar. I charge that electrolyte, and then like a fuel cell, going the other way, I pull the electrons back off, and I can basically just keep pumping back and forth through this system, charging one way, discharging the other. The amount of storage I have is determined by the size of the tanks of electrolyte for storage. And the capacity of the system, the amount of generation I can generate, is determined by how much membrane space I have to be able to pump the material through and pull off the electrons. Flywheels. You'll see flywheels used for a lot in areas where I cannot afford even a second of downtime. So think of a hospital situation where I've got backup power and I've got backup gensets, but I've got people in critical life support equipment, and I can't afford to have maybe 10 or 15 seconds for that genset to spin up, because it takes time for a generator to start, just like your car, come up to speed and start generating power. So a lot of hospitals, for instance, will use flywheels. It's just a big spinning mass. So I keep the thing spinning, and once I get it up to speed, it takes very little energy to keep it spinning. And if I lose the grid, basically it just runs that motor as a generator instead and generates power, typically long enough for the genset to be able to spin up to speed and take over for it. So I have a smooth, bumpless transfer of power for those facilities. You'll also see flywheels used in data centers at times too. Starting to see more uninterruptible power supplies now with a battery solution doing that. But flywheels are still a pretty economical way of handling that. And if I have a very, very good bearing in that thing, they last for a long time versus the wear and tear I see on battery systems. And finally, the other big generation we have is hydro. The other interesting thing about hydro though is I can use it as both a generation source and I can use hydro as a storage source. So how do I use hydro as a storage? Well, if I have a reservoir and I have a water tank and I have a solar installation and I generate solar during the day, I can pump water into the tank, I can pump water into the reservoir, and then when I need the power, when I don't have that solar, I can discharge from the reservoir through my turbine for my hydro system. Roughly 16% of the storage in the United States right now is hydro storage. It's water storage. And most people don't realize that. So the one thing about every energy source we've talked about is if they're acting as distributed generation, they all require a grid connection. Why? Why do I need a grid connection? They all generate energy. If they generate energy, they should be good, right? Well, that's where we need to look at the difference between those distributed generation capabilities and a microgrid. So what's different about a microgrid? Typically, those distributed energy resources require the grid to act as a voltage and frequency reference. Something has to tell me what 120 volts is and what 60 hertz is. It has to tell me what 480 volts is and 60 hertz is. Without the grid, there's nothing there to act as a reference. I need something else to take the place of the grid to do that. Unlike those grid-tied sources, so if I put a PV array on my house with an inverter, and I tie that into my home's power system, if the utility goes down, my house goes down. That inverter is not meant to act as a reference source. So for a microgrid, those distributed energy resources, the microgrid can generate its own voltage and frequency reference. So basically it takes the place of what the grid would be supplying to that installation. This is what allows the microgrid to disconnect from the main grid or island. It can act as its own distinct energy supply. This ability to provide voltage and frequency reference makes a distributed energy resource something called an anchor resource. Now here's an interesting fact about the main utility grid. The main utility grid uses itself as an anchor resource. So let's think about that for a minute. So unless I have the grid available, if the grid goes down, I need something to act as an anchor resource to start the grid back up. If you go back about, I want to say 10, 15 years ago, there was a major power outage in the northeastern part of the United States. Something on the order between the US and Canada of 30 million plus customers went without power for a series of days. And what happened is an oak branch hit a transmission line, tripped a recloser. That's the little guy that isolates that section of line from the rest of the grid, which then cascaded a whole bunch of errors upstream from that through some bad decisions and some bad software that basically took the whole northeastern corridor down all the way up through Newfoundland. Now, there were a lot of power plants in there outside of that, but the problem is those power plants relied on the grid, and when the grid went down, there was nothing the power plant could use for a voltage and frequency reference, so it couldn't start up until its section of grid saw power again. So if you have a power plant, you need to be able to do something called a black start. And a black start is that ability to have this reference that we're talking about. So if I'm the Green Bay power plant, for instance, and the grid goes down, there's a whole bunch of safeties that drop in because I can't keep dumping coal into the boiler. I can't keep generating steam. I can't keep turning turbines because there's no place for any of that to go. So the plant shuts down. To start back up, I have to open valves, I have to close valves, I have to have conveyors fired up, and I need energy to do that. So if a plant has a black start capability, typically what they'll have is they'll have a small genset that they'll fire up. That small genset starts running. They then have a larger genset that's big enough to fire the plant up that ties to that small genset. The small genset is the anchor. The big genset now matches that. It parallels to that and uses that for its reference. And there's now enough power in that big genset to start opening and closing valves and running conveyors and bringing that power back online to the power plant, so the power plant can now start re-electrifying the grid section by section by section. A lot of power plants don't have that black start capability. Again, we need an anchor resource. And sometimes the grid itself needs an anchor resource because it goes down. And it takes time to bring that back up. So as you look at a microgrid, here's a good example of things that, typically can be in a microgrid, right? I've got some form of generation. I've got some wind here. I've got a diesel generator here. I've got some solar. I've got a way to store energy. That's the other thing. I have to be able to store it, right? Because we already talked about the fact that the sun doesn't always shine, the wind doesn't always blow. Hopefully one is happening when the other isn't, but I can't rely on that. So I want some way to store that energy. And if I want to be extremely resilient, I want some other generation capability that I can rely on just in case I don't have enough between all of this. We talked about having some loads because I got to have some place for the energy to go. And I may or may not have a connection point back to the main grid. But the important thing is if I open this connection point, all this keeps working. That's what makes it a microgrid. I'm able to generate a reference and keep on running. So why would I want a microgrid versus distributed generation? Well, first of all, like my home, if I want resiliency in my house, I want to have a microgrid because if the utility goes down, I want to still keep the lights on. I want to keep the refrigerator running. I want to keep the freezer cold. So I'm looking at, I want resiliency. I want utility independence. I don't have to rely on the grid. I'm able to generate power alone. I might be in a location where I don't have a utility. Maybe I'm in the foothills of a mountainous area. Maybe I'm in farther northern Wisconsin. Maybe I talk to the utility and it's going to cost me $200,000 to $300,000 to get a line pulled into my property versus dropping a small microgrid installation onto the property myself. I want to support mission critical loads. I'm a manufacturing plant and I do heat treating. Or I'm a cheese plant and I make cheese. And if I have a 10 or 15 minute outage, I have a $250,000 worth of cleanup and lost product that I'm going to incur because of that power that I lost. So I want to make sure on those critical processes, I have the ability to generate power to keep those running. And last, and I think most importantly, I want something that's more environmentally friendly. I want something that's greener. I want something that involves renewable energy, something that's not fossil fuel, that's not contributing to my carbon footprint. I'm going to pause for a minute, Chuck, and see if there's any questions. And your mute's on.
Sorry, thank you.
I'll keep you honest.
Thank you, sir. No new questions yet. I'm jotting myself some for later on though, so we'll see how it goes. You may continue, please.
All right, thank you. So we've talked about the why. Why does this stuff make sense now? We've talked about kind of the what is distributed energy? What is a microgrid? What is distributed generation versus being able to run independently from the grid? So where are we going with all this? So a lot of it, it's nice. I can use it in limited cases, but we're getting seen more and more of it. So where are we going? First of all, the grid's going to have to grow beyond an energy push system. So let's think about how the grid is initially designed. The grid is made to push power out. and to do that relatively reliably and dependably and across big areas. It's a one-way street though, right? It pushes things out. There's nothing that comes back to it from a communication standpoint by nature, by original design. So first of all, we need to make sure it's a two-way system. Energy can flow in and it can flow out from sites in a controlled fashion. Remember, if you remember a few slides ago, we talked about doing interconnection studies with utilities. If we have a large amount of generation, to make sure they can handle that power coming back to them and they have someplace to go with it if we're not utilizing all of it locally at times. That's part of that two-way system, that flow. I need to not just be able to push energy out, but I need to take energy back into my system. Next, I need some intelligent grid management. I need some two-way communication. Just because you at your distributed generation site, at your microgrid, can generate the power and push it back to the line doesn't mean I have any place to go with it. So the thing we have to keep in mind when we generate electricity, it's fine to generate electricity, but it needs a load. And without a load, things can go bad really quick. Things heat up, things don't work very well. If I don't have enough load on a line, voltage is going to increase. If I have too much load on a line, voltage will decrease, frequency can shift. So it's a very narrow window the utility needs to operate that voltage and frequency on. So you need some way of two-way communication. The other thing is, I want the utility to be able to tell me from my economic benefit when they need my energy too, because maybe I have a big battery system and I have energy stored on site that I'm willing to give back to the utility to sell to them because I don't need all of it right now. Well, the utility needs to know that I have that available and when that's available. So I need two-way communication. I need to be able to say, hey, I've got power, and the utility needs to say, give it to me. Or the utility needs to be able to go to my system and say, do you have any power? And I have to be able to say, yes, I do. I can give you this many kilowatts for this period of time. Okay, great. I'm going to need that about 3 o'clock this afternoon. Okay, thank you very much, Mr. Utility. I'll give that to you. So what we're talking about is moving to what we call a smart grid. Grid right now, to a large part of the way that it operates when we're talking, I'm not talking about the bigger generation sources, but the smaller distributed sources, it's dumb right now. We need to move to a smart grid. So why does this lead to a smart grid? So one, utility and grid operators are gonna have to rethink how and what type of investments in assets are made. It's not becoming cost effective for them to continue to build big coal-fired power plants, big natural gas peaking plants, and they're seeing that. They're seeing that, you know what, it makes more sense to put in renewables. It makes more sense to do PV. It makes more sense to do storage because it's a lot quicker, it's a lot cheaper, and we can respond to changes in our demand much easier and faster than building larger power plants. But it also needs to change the way utilities are thinking because they're going to become less of a generation source and more of a resource manager, right? Rather than generating all the power themselves or buying the power from bigger generators, they're going to be utilizing power from all different places. So they're going to be basically managing traffic within their network, within the grid. So they're going to be traffic managers more than resource generators. Many customers are going to source on site. Got to be able to handle that and that communication, that exchange. So they're going to need to work interactively. They're going to have to be that traffic manager. We got to stop thinking about the grid just pushing things out and think of it more as a rail system, right? Where I need a traffic manager to manage the trains coming back and forth on those branches. So what else is involved with a smart grid? Well, I'm going to need more front-end intelligence. I need a way to know how much energy is available. And I need a way to know how much I can use of that available energy. I want to be able to predict that though too. So I'm going to do more predictive analytics. I'm going to have something called a digital twin. So that's one thing that we're in the process of developing. Is basically it's a computer simulation of the energy installation that I build And so based on weather conditions and based on demand conditions, it can tell me how my grid is going to respond, what it's going to have available, and what potentially I can utilize in other places besides on my site. It's going to use artificial intelligence to be able to do that. So we need to build the correct models, the correct algorithms to be able to handle that. We're going to have to do better demand modeling. So the big utilities do demand modeling now. In fact, I just sat in on the quarterly meeting for the 4 or 5 major sections of the grid within the state just this week, or not within the state, within the country, excuse me, and on what their models are predicting, where they think they're going to be heavy or short on energy, and how they're going to share energy between themselves to make sure they've got enough to meet demand in those areas. And some areas where they say they can't, that's when you start looking at things like California with rolling blackouts, right? So better demand modeling. I want to be able to control demand. So when I increase the output of behind the meter sources, if I put in a battery and solar installation and I have excess power, the utility wants to know that, right? Because they want to know they can tap into that if they need it. And just think, if I have that and Chuck has that and 42 other homes within our area have that, think how much energy potentially can be stored in those 42 locations. Even though they're small systems, we can aggregate those into a larger system and dispatch that energy back to the utility when they need it and help reduce the amount they have to run that natural gas plant or the amount they have to put out from that coal-fired plant and how far they have to fire that up. I can also use it to shut down non-critical systems and do load management. So we're going to talk in a few minutes about the Buboltz Nature Preserve up here in Appleton and the microgrid we've installed there. But an important component of that microgrid is not the fact we have a microgrid and we supply power to the site, but the fact that our microgrid integrates with their facilities. So if we know we're going to be short on energy, we can interact with the building management system and tell the building management system, hey, you know that booster coil you use to preheat air coming into the building on the makeup air unit, could you cut that back by 20%, please? And the building goes, yeah, sure, I can handle that. I can make that up in other ways that are not going to be as burdensome to you, sure. And it cuts back on that, and when I can increase the load, it increases. Or I can look at the weather and say, yeah, you know what? It's going to be it's January, it's going to be really cloudy, and it's going to be cold tomorrow. So, building system, do me a favor. Instead of firing up the microturbine at 8 o'clock when everybody comes into work, could you fire it up at about 5 and preheat the building and start to charge my batteries for me? And overheat the building. So maybe I normally run the building at 72, but it's going to heat it to 75 and store some of that thermal energy in the building because that's going to decay slowly over time. People are going to come in from outside. It's going to be 75 instead of 72, and it's going to feel great to them. And it's slowly over time going to drop down to that 72 set point over a period of 3 or 4 hours. But during those 3 or 4 hours, I have very little electrical demand. So the small amount of solar I am getting is fully charging my battery so that by 11 o'clock when that demand picks up, I'm able to compensate for it. So I can store thermal energy within the building fabric itself. But I need good interaction between my energy generation and my building systems to be able to do that. I can shift usage. I can lower lighting levels. I have occupancy sensors, for instance, at the Nature Preserve in all the rooms in the building. And if no one's in the room, I'm able to drop the lighting levels. And I'm able to continue to monitor it over a period of time. I can drop that level again. And finally, I can turn the lights off if I need to. Within the parking lot, I have motion sensors that tell me if there's anybody within the parking lot. I keep the lights high next to the building at night for security. But the rest of the parking lot goes dark. If somebody drives in, the lights light up on the path they're driving in through the parking lot instead of the whole parking lot coming up. Can lower and control my lighting levels. So what are the benefits if I have a smarter grid? I get more efficient transmission of electricity. So remember we talked about those line losses, talked about, you know, how inefficient the electricity can be at the plug in my home and in my business in Wisconsin. If I transmit closer to where I'm utilizing the power, if I have the source close to where I'm utilizing the power, I cut back on all those line losses, first of all. So now, right off the top, I'm much more efficient. I'm also having a lower carbon footprint. Even if I have the same amount of carbon I generate per kilowatt hour, if I'm closer to my delivery point, I'm more efficient and I'm a lower carbon footprint because I get better efficiency. I can more quickly restore electricity after power disturbances. So like we talked about that major outage in the northeastern corridor of the United States, when that happened, it took 3 or 4 days in some locations to get power back on because I had to bring up section by section by section of grid with the grid supplying itself. But now if I have more distributed generation, I can start bringing smaller sections up more rapidly. Can reduce operations and management costs for the utility and ultimately lower power costs for consumers. If I'm not building big power plants, but I'm utilizing all these other resources, I don't have that capital investment in generation. So I can help drive my costs down because now I'm controlling the grid instead of generating the grid. I can reduce peak demand. So if the more systems I put in place that handle that excess load during the day, especially with solar, the more my overall demand is going to lower, which again helps lower electric rates because I don't need to have as much just in case capacity if I can lower that peak. It's going to give me increased integration of large-scale renewable energy systems. So if I'm able to have a smart grid, if I'm able to talk with the utility is able to talk to me, and it's able to use all that power more efficiently, it's going to be easier to integrate large amounts of storage, large amounts of PV, large amounts of wind into the system. And again, that gives us better integration of those customer-owned power systems, including our renewable energy systems. So what are the challenges? Difficult road for utilities and grid operators. They need a new business model, right? They're used to being generators and purveyors. They got to get used to now the idea of not so much generating, but managing traffic. And how do I handle that? How do I set up that infrastructure to do it? How do I look at energy delivery? How do I look at resiliency? How do I look at those demand charges? How do I shift that demand charges? How do we ensure that I have the right power quality? And how do I handle those system and asset management concepts? You know, how do I look at my coal plant and go, how do I retire this thing now? I mean, I've got a cost model that says I'm going to pay for this over 20 years, and you're telling me I should retire at 10 years, excuse me, early. How do I recover that cost? How do I handle that resource planning? How do I handle dispatch? How do I tell your system to give me power when I need it and know how much power is available? So what are we doing to bring the future to today? How are we doing this? So I'm going to talk about the nature
Steve,
preserve. Yes, Chuck.
Now I found my mic. I'm going to interrupt. A couple of questions that will probably just meld right into what you're going into here. So we have one question from David about how micro can a microgrid be? What's the minimum size? And then a related question, what does a microgrid look like? What is that? Can they put a picture in our mind's eye? Maybe this is exactly where you're going, perhaps.
Sure. So we can talk about that on the macro microgrid scale and the nano microgrid scale. How's that?
Very good.
Yeah. In fact, I've actually had the smallest microgrid that I have worked on designing was 400 watts. And that was for a lighting and power, so it's a recent thing. So, you know, as we know with COVID, a number of companies are trying to get people back to work in manufacturing locations, but they want to make sure their workforce is safe. And so they're doing screening before people come into work. I'm doing temperature screening, filling out questionnaires, every employee before they come in for a shift. And so there's a few businesses we've been working on setting up basically screening tents outside of their entrances. If they are a bigger plant, they have multiple entrances. And quite often those are in areas where it's difficult to get power to. So we actually designed a little microgrid to provide lighting and power for the temperature screening devices within that tent structure with a little small single solar panel array with the microgrid controls and the battery system to supply the power on those individual tents. So that's probably the smallest unit to date I've ever worked with, is about 400 watts. Biggest unit, we're talking utility scale, and anything in between. And as an example, we can talk about the nature preserve up in Appleton. So Gordon Bubol's Nature Preserve, a little commercial for them. It's a 350 roughly acre site. It's been there since the 70s. I used to go cross-country skiing there when I was a kid with my uncle's family, because I lived in Wapaka, but they lived in Appleton. I'd visit them. They have snowshoeing, they have hiking trails. It's a gorgeous, gorgeous site. They do a lot of programming on nature, conservancy, environmental issues, and energy. And they were building a new facility. We got involved, built a new 18,000 square foot lodge and program facility. And as part of that, we said, you know what, if you would let us, we will build a microgrid on site. We will host it. You can use it for educational purposes. And we want to use it as our working lab to educate the public and our own employees on microgrid technology and distributed energy technology. They said, boy, this sounds great. And so we did that. So the site is totally powered by the microgrid. In fact, we're in the process this fall of becoming totally grid independent. We still have a grid tie. We are going to separate entirely from the grid, hopefully by the end of this year. So we have 200 kilowatts of solar. We have a 60 kilowatt Kohler natural gas generator. We've got a 100 kilowatt battery. We've got an electrolyzer and a 25 kW fuel cell to utilize the hydrogen from that electrolyzer. And we've got a 65 kilowatt micro turbine that's located at the lodge itself that we utilize for combined heat and power on a hydronic system in the lodge. So how does this system working? So I took a snapshot this morning of the facility. So this is basically our control room and our learning center. We call it our immersion center because we're able to immerse people within the technology. If you go into this facility, there's a wall halfway through the facility, which is a big glass wall, and all the technology sits behind the wall. So you can come there, you can look and see what the battery systems look like. What does an electrolyzer look like? What do inverters look like? What is the power distribution, the controls, everything with this. And we have all our individual components. So what we can see here is this morning, nobody was in. They were down this morning, so we're just maintaining the building envelope itself. We had about a 15 kW demand. It was a very cloudy day. We had 90% cloud cover up here this morning. Unfortunately, it was really nice and sunny yesterday. We were generating about 9.5 kW of solar. We were pulling another 10 kW from our fuel cells, from our hydrogen tank down here. And basically the excess we were taking out to our battery to help float the system and buffer the system to take care of any load fluctuations. So this would be a moderate sized microgrid. It's not huge. It's about a little less than half a megawatt total of generation capability. And to your point, Chuck, asking about sizing, as another example, this unit is our escape cabinet, our ESC 2.0 cabinet. This can be as small as about 7 kilowatts. It can go as big if we string multiple units together up to about 60 kilowatts. This is an entire microgrid control and storage solution stood up in a single box. So this is about 3 feet deep, about 9 feet long. This could power my house. If I have 14.4, I could power my house off from solar and the battery storage indefinitely without a generator. This unit is also designed to be plug and play too, so it's rapidly deployable. So I can set it in place on a site. I can put in 2 pre-assembled ground mount solar arrays, plug those in with quick disconnects to the cabinet, set a small 20 watt or 20 kilowatt, excuse me, generator on site, plug that in also, and then terminate back out to my loads. I can set this whole system and have it up and running in less than half a day with 2 people. This is enough to power roughly about 5 typical Wisconsin homes and small commercial building. So picture something on the size of a convenience mart or something like that. Excuse me. And again, important thing, it's a microgrid, right? So it can be grid tied, or it can be totally independent, or it can transfer automatically if I lose power.
Yeah, I'll just take a minute again, Steve, here. I see we're at about 15 minutes total, and I'd like to reserve about 5 minutes at the very end just to talk about what we're doing locally here, just to inform people on this energy district. So just to give you a little, I don't know how many more slides you have, Steve, to give you an idea.
Yep.
We do have a couple a couple questions from Gene. Several people, I presume, that are on this webinar listening to you have gotten interested in all of this energy business because people were, we've had an issue with this Cardinal Hickory Creek transmission line coming, proposed to come across our Southwest Wisconsin Driftless area here, and that's gotten people interested in this issue. And so the question is, I think you've sort of answered it, but can microgrids help reduce the need for these huge transmission line projects?
And the answer is absolutely. Absolutely. Again, the more we're able to source locally, the less power we have to bring in from outside the area. And if you look in the case of some of the utilities are rethinking the way they generate, and they're thinking on areas maybe they have long distance transmission lines. So if we look at Upper Michigan, for instance, I may have a 3 or 4 mile transmission line to service 4 or 5 homes. And that's a very expensive line, especially up there, to maintain, right? Because I've got ice storms, snowstorms. I end up doing a lot of repairs. It's very expensive to install those lines. And they're looking more and more at being able to install microgrids and supplying those for those smaller communities. Same thing out west in those mountainous areas where there's small mountain communities. Much more cost effective to locate this technology versus running power lines to this. Same thing with cell towers.
Yeah.
In remote locations.
Thank you. A sort of related question here in Wisconsin, from Sandy, is in Wisconsin, is there a monthly fee that a group would have to pay to have an independent grid and or sell the energy back to the utility company? That might be a big question. I don't know.
So as we talked about earlier, with the regulations different within the utility, different within the same utility, what you can or can't sell back and how much generation you can have and still sell back, all depends on the location, the utility that you're connected to. So that has to be really looked at almost on a case-by-case basis. Unfortunately, that's that complex spaghetti of regulations.
Right.
I'm sorry, I lost myself in the first part of the question again, Chuck.
Well, it just was if there was a fee. So the question was, yeah.
Yeah, so a fee. Typically, there's not a fee unless you put a large system in. You do have to file for an interconnection agreement with your utility if you're going to be utility connected. But otherwise, there's no other fees beyond normal permitting fees for any type of construction, that you'd be required to do. If you do a larger system, the utility may require an interconnection study. And a larger system we're talking about is something even bigger than we're talking about right now with the nature preserve, for example.
Mhm.
So most small systems don't require that.
All right. Well, why don't you continue with your presentation then, and we'll maybe another 5 or 6 minutes, we'll try and wrap up this portion of the webinar.
Absolutely. Well, I've got one more slide, and then I'm open for questions.
There you go.
So basically, how does this work in the real world? So yeah, it all sounds good. Sounds great. How does it really work? So September 17th of 2018, the International Association of Electrical Inspectors had their convention in Appleton. And they had a dinner out at the Nature Preserve. The Nature Preserve has two roughly 250 person halls that they can host events in. And we were doing tours of the microgrid for the electrical inspectors that night. And we had a very severe line of thunderstorms pass through the point. We were running shifts of people through because it's a very large group, and we can only take about 20 to 25 people in the control area at one time. So we were cycling people through, and the wind got so bad that two of the guys tried to run from the control room back up to the lodge and couldn't get the front door open because the wind would not allow them more than crack the door open. And the lights blinked a couple times, and we kept on chugging and didn't think of anything of it until the next morning. We read that the utility had lost power in our area during the time we were giving tours, and the inspectors, and we had no idea. So the grid just picked up, kept running, no local grid. And that was fine, you know, that was maybe an hour or so. More interestingly enough, though, last year, if you remember, July 20th to 24th, we had the storms that passed through our area that weekend in north central Wisconsin. We Energies lost about 300,000 customers, about 70,000 homes. In the case of Bubolz, power went out at noon on Saturday from the utility, came back, I believe, midnight on Wednesday night. There were two weddings that were booked at the Nature Center for that day. One of the brides was getting married a small community on the east side of Lake Winnebago. She went to the church. The priest is like, well, we're out of power, so we can't help you girls get ready. So one of their neighbors brought a portable generator in. They powered up a curling iron and a lamp so they at least get their hair done. About an hour before the service, the priest came in and said, you know what, we're going to locate your ceremony to the little church about 20 miles south of us because they have power there because we still don't have power. And we'll redirect people. So fine, they redid that. Got done, left the church. They had a bus for the bridal party. Bus broke down, hit storm damage. Had to wait for another bus. They get closer and closer to the Appleton area, and the bride starts to notice that none of the traffic lights are working. And she doesn't see lights on in any of the buildings. And she finally looks at her father and goes, what's going on, Dad? He goes, I didn't want to tell you, but there's no power in the city of Appleton. And she's like, oh my God, I've got 200 plus guests showing up. And they called the Nature Center. The Nature says, we got power, we have a microgrid. So the Saturdays are normally open at the Nature Center. The staff was working. The staff said the lights blinked once, and they thought there was just a lightning strike someplace close by. What actually happened is that was the microgrid taking over as basically their reference source because the grid was down. They had no idea that they were running from the microgrid, ran that way from noon on Saturday to midnight on Wednesday night with no bumps, no problems. Technology, again proved itself. So as long as we have the right design for the system to match the system to the load, the systems work very dependably.
Yeah, very good. Well, Steve, I'm going to ask you, I'm watching my clock here too. I think, there we go. Questions, comments, good for you.
And there's my email. If anybody wants to email anything else or has any questions maybe that we didn't get to today, be happy to respond to those.
Oh, excellent, excellent. And so folks, those of you that have submitted some chat questions, we're not going to get to all of them, but we will have them and we'll forward those to Steve, and then you can address them as you will, Steve. Thank you very
Be
much.
happy to do that. Thank you,
Thank
Chuck.
you. I think I'll ask a question that I think is in the back of a lot of folks' minds, if you can answer this in 2 minutes or so, because I would like to make a couple of the comments at the end. You know, because of the folks that are interested here, how would we start? I mean, people loosely use the term a microgrid. We should have our own microgrid. Well, what would be the first couple steps if a group were interested in trying to get that initiative going forward here in Southwest Wisconsin?
So the first thing we typically look at if we're going to look at a system is looking at what the load profile looks like. So what is the load? What does the demand look like? If it's a single facility, that's often quite easy. We can either get data from utility bills to give us an approximation. We can get 50-minute interval data quite often from your meters. If it's a number of sites, we can aggregate that data together. So for instance, if there's 4 or 5 meters, a small community that would want to look at something, we can pull that data together. That gives us a profile of what the load looks like, which then tells us, okay, what is the right combination of generation resources to look at and how much storage do we need to be able to maintain that system? And what are we trying to achieve also is the other question we ask, because you may be trying to just lower your electric cost and the amount that you're drawing from the utility and trying to improve your carbon footprint. You may be looking at trying to become net zero carbon. We're currently working on a project in Door County where the goal was, we're not trying to save money necessarily off the utility bill, but when we get done, we want to be net zero. So we want to produce more energy than we use, and we want to make up and compensate for any carbon-based energy we do by producing non-carbon-based energy to compensate for that. Or it could be resilience. I want to make sure that I have power available. Or it could be a combination of all of those things, right? So again, it's understanding, what the primary objectives are for the particular location.
Excellent, excellent. Well, Steve, I tell you, this has been terrific. And for those folks listening again, we are recording this, so we will have this on Driftless Area Land Conservancy website. I'm not savvy enough to put that website up on the screen here or my email address, but you can find that easily at that site if you have questions or want to contact us about that. Beyond that, folks, just want to give you a little update. We are working at the Conservancy to move toward utilizing some of the things that distributed energy resources to develop what we is known as an energy district. We're following a model that's being used successfully in several counties in Northeast Iowa right now, and they are helping guide us in the development of this. We're just in the very initial stages, Jen's going to help us out here. Thank you, Jen. And there's our website. So we have a couple things going here. We're continuing with this energy, our future energy speaker series, and our next speaker will be on May 28th, and this has to do with the property assessed clean energy program that is available to businesses and nonprofits, so people can check that out. Going back to our work on energy districts, we meet regularly. We have some subcommittees working in particular areas of that. We welcome additional people who want to help us move this initiative forward here in Southwest Wisconsin. We're just very excited about lots of opportunities. I think Steve, you've pointed that out to us, that times are changing, and we're right in the middle of a very exciting period, and from my perspective of what can be done so much better than our former models. So with that, Jen Filipiak has been in the background here. She's executive director of Driftless Area Land Conservancy. and helping me out, helping us out, get this whole webinar put together. Have I missed anything, Jen, that needs to be said in the last minute here?
Nope, I don't think so. Thanks for coming, everyone. Join us next time.
All right.
We're getting the hang of it.
Yes, we
Thank
have-
you.
yes, we are. Yes, and I
Thank
will
you,
echo
Steve,
that
very
too.
much.
Thanks again,
Thank
Steve.
you.
You bet. And everybody, and let's move this whole energy conversation forward. Have a great afternoon and
Absolutely.
evening,
Everyone
everybody.
too. Thank you again.
Thanks, Steve.
Bye, everyone.